Hello friends, welcome back to my YouTube channel. Today in this video, I'll be talking about simple distillation. Although I have made videos on simple distillation already there on my YouTube channel, but still I have planned to make 3 more videos where I will be telling you how to use the Raleigh's equation for finding XW, that is the composition of the bottom product. In my earlier discussion on simple distillation, I told you how to use the Raleigh's equation where the integral in the equation was to be solved graphically. So we have done that. I have done that. I'm giving link to those videos in the description section. Today, as I said, I will be discussing about the analytical solution. So at the end of this discussion, we will have an equation which can be used to find XW. So I have given the title analytical solution to this particular video. And then in the other 2 videos, I'll be doing 2 more videos on this topic. And the first one, in the next video, I'll be discussing a numerical where we will learn how to find XW graphically. And then in the next video, I'll be telling you how to use the equation that we get in today's video to find out XW. In short, the 3 discussions that I have planned on simple distillation and particularly on Raleigh's equation will help you to find out XW. So that is the plan for this particular video. Okay, so let us start with knowing the Raleigh's equation. The equation is ln of f by w. That is equal to integration from xw to xf dx upon y minus x. And what are the terms involved in this equation? F is the moles of feed, W are the moles of bottom product, XW is the mole fraction of more volatile component in the bottom product, XF is the mole fraction of the more volatile component in the feed solution, Y is the mole fraction of the more volatile component in the vapor phase, and X is the mole fraction of the more volatile component in the liquid phase. And we are using the values when the liquid and vapor phases, they are in equilibrium with each other. So this is the equation. I have derived it in my earlier discussions on Raleigh's equation or simple distillation. I'm giving link to those videos. So this is the equation. Now the task is to solve the integral on the right hand side of this equation, integration from xw to xf dx upon y minus x. So you have options, 3 options for this, 3 options for solving the integral. First one is you can solve it graphically, and for that, we will be using the VLE data that may be known to us. So on y-axis, you are plotting 1 upon y minus x, and on x-axis, you are plotting x. That is the mole fraction of the more volatile component in the liquid solution. So you may get a curve like this. So you have to mark the limits, xf, and the other limit is x. And this area under the curve is nothing but the value of this integral. Integration from xw to xf dx upon y minus x. So this is one option. I have already discuss this. I have solved a numerical where this approach was used to find the integral. Then second approach is you can use any of the numerical technique for solving this integral. So again, I have made one video where I have used a numerical technique to solve this integral. So I'm giving link to that video as well in the description section. So you can solve it graphically, you can solve it numerically, and the third way is you can solve it analytically. And that is what we are going to learn today. So the important thing for Rayleigh's equation is to solve this integral. So you can solve it graphically like this, or you can use any numerical integration technique for solving the numerical, or you can have an analytical solution. Analytical solution is possible when you have an equation for y in terms of x. So for solving the integral analytically, we need to have an equation for x in terms of equation for y, in terms of x. So we need equation of this kind. And then you can put this equation in the integral and then you can integrate it. You can put y is equal to fx. So you'll have function of x in the denominator and you just have to integrate it with respect to x. That is the approach. So the first requirement is we need to have an equation for y in terms of x. And actually such an equation is the equilibrium relationship. If you have such equation of this form, y is equal to f of x, this would be relating y and x, as it is clear. And y and x, these are concentrations in vapor and liquid phases respectively that are in equilibrium with each other. So such an equation will be the equilibrium relationship. So if equilibrium relationship is provided, if the equilibrium relationship is known to us, then you can have analytical solution for this integral. So such an equation is actually the equilibrium relationship. And today we will learn how to solve this analytically if you have an equilibrium relationship. Okay, so now let us go for the analytical solution. So the equation, Rayleigh's equation is ln of f by w, that is equal to integration from xw to xf dx upon y minus x. And the equation for y in terms of x, what is the equation that we will be using? The equation is very well known to you. The equation is y is equal to alpha ab x divided by 1 plus alpha ab minus 1 into x. So this is an equation which relates y with x. So there is a kind of or this is actually an equilibrium relationship. And in order to use this equation, the most important requirement is alpha ab has to be constant. So you can use this if alpha ab is constant. So let us say that alpha ab is constant, and considering alpha ab to be constant, let us use it in the integral and solve the integral analytically. So once you have the equation for y in terms of x, we are going to use that in the Rayleigh's equation. So you have ln of f by w is equal to integration from xw to xf dx upon alpha abx divided by 1 plus alpha ab minus 1 into x minus x. So in place of x, we have used, in place of y, we have used this equation. So now everywhere you have the equation is now in terms of x. So now let us deal with the integral separately. So for that, I am going to denote the integral by I. So I is equal to integration from xw to xf dx upon alpha AB x divided by 1 plus alpha AB minus 1 into x minus x. Let us simplify this. Therefore, I is equal to integration from xw to xf dx upon alpha AB x, and I have simplified the term in the denominator. So it would be alpha AB x minus x into 1 plus alpha AB minus 1 into x divided by 1 plus alpha AB minus 1 into x. So further I can simplify it in this way. Therefore, I is equal to integration from xw to xf dx upon alpha AB x minus x. So I am multiplying x with the terms in the bracket. So this will be alpha AB x minus x plus alpha AB minus 1 into x square divided by 1 plus alpha AB minus 1 into x. So we have used the equation for y, and we are now modifying the integral, and we are actually putting it in a form that is suitable for solving it analytically. Okay, so we have previously got this equation. I is equal to integration from xw to xf dx upon alpha AB x minus alpha AB minus 1 into x squared divided by 1 plus alpha AB minus 1 into x. So in the next step, this term 1 plus alpha AB minus 1 into x, it goes into the numerator, and that is what I will be doing. So therefore you have I is equal to integration from xw to xf 1 plus alpha AB minus 1 into x divided by alpha AB x minus alpha AB minus 1 into x square dx. And in the next step, what we can do, in the denominator, from the first two terms you can take x common. So if that is done, you have I is equal to integration from xw to xf 1 plus alpha AB minus 1 into x divided by alpha AB minus 1 into x minus alpha AB minus 1 into x square. Further, again in the denominator, you can take alpha AB minus 1 into x, this term common. So if you do that, you will have I is equal to integration from xw to xf 1 plus alpha AB minus 1 into x divided by 1 plus alpha AB minus 1 into x, and in the bracket we are left with 1 minus x. So in this way we have simplified to this form. Further, what we can do, we can separate the denominator. So there are two terms in the numerator, 1 plus alpha AB minus 1 into x. So in the next step, we will separate the denominator. So therefore, you have I is equal to integration from xw to xf 1 upon alpha AB minus 1 into x into 1 minus x plus alpha AB minus 1 into x divided by alpha AB minus 1 into x into 1 minus x. So simply I have separated the denominator, and we have got this particular equation. Okay, so previously we had got this equation. I is equal to integration from xw to xf 1 upon alpha AB minus 1 into x into 1 minus x plus alpha AB minus 1 into x divided by alpha AB minus 1 into x into 1 minus x. Now what can happen? Now if you look at the second term, so alpha AB minus 1 into x you have in the numerator, and you also have the same term in the denominator. So these two terms can get cancelled, and then we will separate the integration. So the next step will be I is equal to integration from xw to xf integration from xw to xf 1 upon alpha AB minus 1 into x into 1 minus x dx plus integration from xw to xf of 1 upon 1 minus x dx. So we have separated the integration and then we have cancelled this term alpha AB minus 1 into x. So you have now two integrals. We are going to denote that by I1 and I2. So you have I is equal to I1 plus I2, and in this case I1 is the first integral, integration from xw to xf, 1 upon alpha AB minus 1 into x into 1 minus x dx, and I2 is the second integral, that is integration from xw to xf of 1 upon 1 minus x dx. So previously we have got this term or this equation, I1 is equal to integration of, we got two integrals, one was I1 and the other one was I2, and now we are going to first solve I1. So I1 in this case is integration from xw to xf, 1 upon alpha AB minus 1 into x into 1 minus x dx. That is alpha AB is constant, therefore you can take this term out of the integral, and we will have I1 is equal to 1 upon alpha AB minus 1 integration from xw to xf of 1 upon x into 1 minus x dx. Now we are going to solve this integral by parts. Integration by parts. We are going to use the approach of integration by parts. So for that, I will denote this term, or I will designate this term in this way: 1 upon alpha AB minus 1 into x into 1 minus x. I will designate it as a upon alpha AB minus 1 into x plus b upon 1 minus x, where a and b are constants, which we will have to find in order to get the solution for this integral. Okay, so in the next step, I'll simplify it. That is 1 upon alpha AB minus 1 into x into 1 minus x is equal to a into 1 minus x plus b into alpha AB minus 1 into x, and divided by alpha AB minus 1 into x into 1 minus x. So you have the same term in the denominator on both the sides, so that will get cancelled. So you have simply 1 is equal to a into 1 minus x plus b into alpha AB minus 1 into x, and I am calling this as equation number 1. Now our objective is to get the values of a and b. So we will start with getting value for a, and for that what is the approach? What you have to do, the term in the denominator where a is the numerator. So the term in the denominator, it's to be equated to 0. And then after solving, whatever value for x you get, you are going to use that in equation number 1. So as I said, the denominator of this term is alpha AB minus 1 into x. Alpha AB minus 1 into x, we are going to equate it to 0. So in this equation 1, we are going to put alpha AB minus 1 into x is equal to 0. That is, x will be 0 upon alpha AB minus 1. That is, ultimately x will be equal to 0. So we are going to use this in equation 1. So it will be 1 into a, 1 is equal to a into 1 minus 0 plus b into 0, because the entire term is 0. So that gives us a is equal to 1. And this is, in this way, you get the value of the first constant, that is a. Now in order to get the value for b, we are going to equate the term in the denominator to 0. So we will do that in the next step. Okay, so we got a, value for a. Now let us get value for b. So for that, we are going to equate the term in the denominator, that is 1 minus x is equal to 0. So we are going to put 1 minus x is equal to 0 in equation 1. That is, we are going to use x is equal to 1 in equation 1. So if we do that, it will be 1 is equal to a into 1 minus 1 plus b into alpha ab minus 1 into 1. 1 minus 1 is 0. So it will be 1 is equal to a into 0 plus alpha ab minus 1 into 1. That is 1 is equal to b into alpha ab minus 1. That is b is equal to 1 upon alpha ab minus 1. So in this way, we get the value of b. So now we have values of both the constants with us. A is 1 and b is now 1 upon ab minus 1. Okay, so we had this equation 1 upon alpha ab minus 1 into x into 1 minus x is equal to a upon alpha ab minus 1 into x plus b upon 1 minus x, and we have just got the values of a and b. A, it as 1 and b was 1 upon alpha ab minus 1. So we are going to use these values in this equation. So it will be 1 upon alpha ab minus 1 into x into 1 minus x, that is equal to 1 upon alpha ab minus 1 into x. We have used the value of a, and then now we will be using value of b. So it will be plus 1 upon alpha ab minus 1 into 1 minus x. Now let us integrate on both the sides, and we will use integration for a separate integration for the two terms on the right hand side. So it will be integration from xw to xf dx upon alpha ab minus 1 into x into 1 minus x, that is equal to integration from xw to xf dx upon alpha ab minus 1 into x plus integration from xw to xf dx upon alpha ab minus 1 into 1 minus x. And on the right hand side, this term, the integral on the right hand side is nothing but I1, the notation that we used for this integral earlier. So you have, or you can take the constant terms out. So it will be integration from xw to xf dx upon alpha ab minus 1 into x into 1 minus x, that is equal to, now alpha ab minus 1 is constant, so that will come out of the integral. So it will be 1 upon alpha ab minus 1 integration from xw to xf dx upon x plus again 1 upon alpha ab minus 1, the constant term is out of the integral, into integration from xw to xf dx upon 1 minus x. And the term on the left hand side, is nothing but I1. So therefore now we get I1 as I1 is equal to 1 upon alpha ab minus 1 integration from xw to xf dx upon x plus 1 upon alpha ab minus 1 integration from xw to xf dx upon 1 minus x. Okay, so we had got this. We have I is equal to I1 plus I2. We just got equation for I1, and now we are going to use I1 and I2 to get the final integral, that is I. So I1 is 1 upon alpha ab minus 1 integration from xw to xf dx upon x plus 1 upon alpha ab minus 1 integration from xw to xf dx upon 1 minus x. We just got it. And I2 is integration from xw to xf 1 upon 1 minus x dx. So let us use this equations, and therefore you'll have I is equal to 1 upon alpha ab minus 1 integration from xw to xf dx upon x plus 1 upon alpha ab minus 1 integration from xw to xf dx upon 1 minus x plus integration from xw to xf 1 upon x dx 1 upon 1 minus x in dx. So that is I is equal to 1 upon alpha ab minus 1 integration of dx upon x is ln of x. So ln of x with limits xw to xf plus 1 upon alpha ab minus 1 integration of this is dx upon 1 minus x is ln of 1 minus x divided by the coefficient of x. In this case, coefficient of x is minus 1. So it is ln of 1 minus x upon minus 1, and the limits are from xw to xf. And there is another term. Again, the integration is ln of 1 minus x divided by minus 1, and the limits are xw to xf. In the next step, we are going to apply these limits. So I hope you know the rules of integration. And the integration of 1 upon x or dx upon x is ln of x. And integration of 1 upon 1 minus x. Here 1 minus x is function of x. So it will be ln of that function divided by the coefficient associated with x. And in this case, the coefficient associated with x is minus 1. Okay, so previously we got this I is equal to 1 upon alpha ab minus 1 into ln of x limits xw to xf plus 1 upon alpha ab minus 1 ln of 1 minus x divided by minus 1 limits xw to xf plus ln of 1 minus x divided by minus 1 limits xw to xf. Now let us apply the limit. So it will be I is equal to 1 upon alpha ab minus 1 ln of xf minus ln of xw after applying the limits, minus this plus, that it becomes minus. So minus 1 upon alpha ab minus 1, and now the limits are applied, ln of 1 minus xf minus ln of 1 minus xw. Again this minus this plus becomes minus, and now limits are applied, ln of 1 minus xf minus ln of 1 minus xw. And in the next step, we are going to use one logarithmic identity. What is that? Ln of m minus ln of n is ln of m upon n. So we are going to use this logarithmic identity over here, and also over here. So let us do that. Let me erase it. I hope you know this logarithmic identity. So it will be I is equal to 1 upon alpha ab minus 1 ln of xw by xf by xw, the logarithmic identity, minus 1 upon alpha ab minus 1 ln of 1 minus xf divided by 1 minus xw, the logarithmic identity used, minus ln of 1 minus xf upon 1 minus xw. Now, in the next step, from the first two terms, we can take 1 upon alpha ab minus 1 common. And if you do that, it will be I is equal to 1 upon alpha ab minus 1 ln of xf upon xw minus ln of 1 minus xf divided by 1 minus xw plus the other term. Now, while making plus, I am interchanging I'm taking reciprocal of the term, this term. So if I do that, it will become plus. So it will be minus, because it will be like this, minus, and now I'm interchanging the limits, minus ln of 1 minus xw divided by 1 minus xf. Just a minute. So this is 1 minus xf. So I have used it. So this minus, it becomes plus, and that's why you have plus sign over here. So you have I is equal to 1 upon alpha ab minus 1 into ln of xf upon xw minus ln of 1 minus xf by 1 minus xw plus ln of 1 minus xw divided by 1 minus xf. So in the next step, what we will do, again you can use the logarithmic identity. Ln of m minus ln of n is ln of m upon n. And that is what I have done over here. Therefore, I will be equal to 1 upon alpha ab minus 1 into ln of xf upon xw divided by 1 minus xf upon 1 minus xw plus ln of 1 minus xw upon 1 minus xf. Okay, so we got this. I is equal to 1 upon alpha ab minus 1 ln of xf upon xw divided by 1 minus xf by 1 minus xw plus ln of 1 minus xw by 1 minus xf. Now I'll simplify over here. So it will be I is equal to 1 upon alpha ab minus 1 ln of xf into 1 minus xw divided by xw into 1 minus xf plus ln of 1 minus xw by 1 minus xf. Now this is the integral, final equation for the integral. You must be remembering you had the Raleigh's equation ln of f by w integration that is equal to integration from xw to xf dx upon y minus x, and we had designated this integral by I, and now we have got equation for I, or we have got solution for I, solution for the integral. So if I use that in the Raleigh's equation, the Raleigh's equation will now be ln of f by w is equal to 1 upon alpha ab minus 1 into ln of xf into 1 minus xw divided by xw into 1 minus xf plus ln of 1 minus xw upon 1 minus xf. So this is the analytical solution for the Raleigh's equation. So you can use it to get xw, or even if alpha ab is known to you, you can solve it to get w if all other quantities are known to you. So you can use as per your requirement this equation. So this is the analytical solution for the integral on the right hand side of the Raleigh's equation. Further, you can simplify it like this will be ln of f by w, and I'm bringing this term on the other side. So if I take this term on the left hand side, it will be minus ln of 1 minus xw divided by 1 minus xf, that is equal to 1 upon alpha ab minus 1 into ln of xf into 1 minus xw into 1 minus xf. Okay, so we got this previously, ln of f by w minus ln of 1 minus xw divided by 1 minus xf, that is equal to 1 upon alpha ab minus 1 into ln of xf into 1 minus xw divided by xw into 1 minus xf. So what I'm doing, I'm trying to put it in another form which can be more useful for solving numericals based on simple distillation. Okay, so on the left hand side you can use the logarithmic identity ln of m minus ln of n. So it will be ln of f by w divided by 1 minus xw divided by 1 minus xf, that is equal to 1 upon alpha ab minus 1 into ln of xf into 1 minus xw by xw into 1 minus xf. So you can simplify on this side. So it will be ln of f into 1 minus xf divided by w into 1 minus xw, that is equal to 1 upon alpha ab minus 1 into ln of xf into 1 minus xw divided by xw into 1 minus xf, that is alpha ab minus 1 into ln of f. So this alpha ab minus 1 is brought on this side, so it will be alpha ab minus 1 into ln of f into 1 minus xf divided by w into 1 minus xw, that is equal to ln of xf into 1 minus xw and xw into 1 minus xf. Okay, we just got this equation, alpha ab minus 1 into ln of f into 1 minus xf divided by w into 1 minus xw, that is equal to ln of xf into 1 minus xw divided by xw into 1 minus xf. So in the next step, what I will do, I will multiply this logarithmic term with each term in the bracket. So it will be alpha ab into ln of f into 1 minus xf divided by w into 1 minus xw minus ln of f into 1 minus xf divided by w into 1 minus xw, that is equal to ln of xf into 1 minus xw divided by xw into 1 minus xf. And in the next step, I'll bring this term, I'll take this term on the right hand side. So it will be alpha AB ln of f into 1 minus xf divided by w into 1 minus xw, that is equal to ln of xf into 1 minus xw divided by xw into 1 minus xf plus ln of f into 1 minus xf divided by w into 1 minus xw. And in the next step, I will use another logarithmic identity, which is ln of m plus ln of n is equal to ln of m into f. So I'll be using this logarithmic identity. So it will be alpha AB ln of f into 1 minus xf divided by w into 1 minus xw, that is equal to ln of xf into 1 minus xw divided by xw into 1 minus xf into, now this term, into f into 1 minus xw divided by w into 1 minus xw. So what is going to happen? 1 minus xf, these two are going to get cancelled, and 1 minus xw is also going to get, the two terms are going to get cancelled. So you are left with alpha AB into ln of f into 1 minus xf divided by w into 1 minus xw, that is equal to ln of xf into f divided by xw into w, that is ln of xf into f divided by xw into w, that is equal to alpha AB into ln of f into 1 minus xf divided by w into 1 minus xw. And this is another form which can be used to get xw or for getting any other quantity like w. So this is another form of analytical solution for the Rayleigh's equation. So in this way, we have ultimately got the analytical solution. So with this, I end my discussion for the present topic. In my next two videos, I'll be solving numericals, where we will learn how to find out xw. In the first video, I'll tell you how to find xw graphically, and in the second video, I'll tell you how to use the analytical solution to get the value of xw. So thanks for watching my video. I hope you have understood the concept. If you have any doubts, you please mention them in the comment section. Do subscribe to my channel. Tell your friends to subscribe to it. And don't forget to hit the bell icon so that you'll be notified as soon as I upload any new video. In my next video, I'll be discussing a numerical where we will learn to find the value of xw. So for now, thank you. Thank you for being with me. Have a nice day and hope to see you soon in my next video.